how streaming works. Streaming is a very important part of Hadoop. So what it allows us to do is to use programs other than Java. For example, if you want to use Ruby or Python or some other language like C++, and you have an executable for it, you can actually use Hadoop to actually run executables which are created in those languages. So we'll go over today the definition, the execution process, what's the syntax, what are the various options available, and some examples. So the way we've structured it, we are going to start off looking at some theoretical aspects, and then finally I'll take the practical examples and run them and show you how they work on Ubuntu. So first of all, the definition says that Hadoop streaming is actually used to create and run MapReduce jobs, which with any executable or a script as the mapper and or the reducer. What it means is that you can actually create an executable in any language. It doesn't have to be Java. And then you can submit it to the Hadoop streaming utility, which will use the mapper and the reducer to create some processes that will run the executables that you supply. So what's the overall execution process? So like I stated, so it's going to create a MapReduce job, submit the job to an appropriate cluster, and then monitor the progress of the job till completion. So really there are two components involved. The first is a mapper. So what does the mapper do? The mapper's job is to actually launch an executable as a separate process. So the mapper is going to start up a process. The process will take as input some lines that the mapper is going to feed to it from an input folder, and then the process will send an output back to the mapper. The mapper collects the output from the process, the mapper process, and then sends that output over to the reducer, and the reducer further takes that output which has been sent from the mapper, it processes it, and then sends its own output over back to the reducer process, and then the reducer process basically sends it back to the utility that puts the output into an output folder. So what's to be noted over here is that both the mapper and the reducer processes work with std_in and std_out, so standard input, standard output. So it's important to make sure that the mapper and the reducer programs that you write should be created as executables. So besides the mapper, there's this reducer process. The reducer process works pretty much the same way as the mapper with some difference. So just like the mapper, the reducer also launches an executable process. The executable process will take as input the key value pairs that will come out from the mapper, and it will send its own output onto standard output. And basically the standard output is going to be some key value pair again, and the key value pair is then pushed into a output folder. So this is what the whole process looks like. If you look at it, there's an input directory right here on the top. The input directory is going to contain one or more than one files. Then the files are processed by the mapper line by line, and it sends those via the standard input to the mapper process. The mapper process then, after doing its own processing, so this mapper process essentially will be running the executable that we supply. It will send its output to standard output, which is again collected by the mapper, and the mapper sends the output and key value pairs to the reducer. The reducer then sends its input to the reducer process through standard input, and the reducer process churns out to standard output whatever it sends out as key value pairs, which finally end up in output directories by Hadoop. So now we'll take a quick look at the syntax. So this is what the syntax is for the streaming utility. Out here you see it's Hadoop, a jar, the jar command, the path to the streaming.jar file. So depending upon which version you're using, the streaming jar command is going to look a little different. And there are two types of options that you can supply. One is the generic option, the other is streaming. So the generic options have to be placed before the streaming options. That's the point to be noted. And streaming options are having some options in it which are mandatory, and there are some of them which are optional, and all the generic options are actually optional. So we have this as the syntax. So we see Hadoop jar, and then in 2.6.0 the streaming utility is actually residing in this particular folder, share. So you have to give the full path name and supply the input folder name and the output folder name, and tell which particular executable should be run as a mapper, and then you supply which particular executable should be run as a reducer. In this particular example here, we are using cat as the mapper and WC, which is word count, as the reducer. So we'll see in a while how we can use the Unix applied cat command and the word count command as the mapper and the reducer respectively. The cat command simply takes as input um, any file, and then it prints out the output to the screen or the standard output. And the reducer, which we are going to use, is word count. So word count is a standard utility. What it does in Unix, it allows you to see the sum of the number of words or the number of characters, number of lines inside any given file. So we see this is again showing it's being showed as a backslash over here, because essentially in Unix, whenever your line spills over to another line, you can backslash acts as a continuation character. So if you have a long command to be typed in Unix, you at the end of the first line you can just put a backslash and keep continuing with the command line. So like I said, there are two different types of options: streaming options and generic options. All the generic options need to be specified first. We are going to talk about streaming options first in our case, because there are some mandatory ones. Now, the required arguments for streaming, there are 4 of them. One's the input, which means what's going to be your input folder, which is containing the directory. So it's the directory name, which will supply the file that is containing all the lines that need to be processed. So there could be one file in the directory or more than one file. So you need to specify the input folder, the output folder, or the directory, right? And the mapper executable, or the Java class name, and the reducer executable, or the Java class name, right? So the next thing that we have to know is what are the optional arguments for streaming arguments. So there are some optional arguments that you can give. One is the file name. So if you give the file option and give a file name, this is nothing but the executables that you're supplying. So what's going to happen is these executables will get deployed to the compute node. You can also give and specify which particular Java class name you're going to use. As we proceed in our course, we'll be learning more about the different types of input format, output formats that we can use. But essentially, if you don't use the default, which is text input format, for the input and the output format Java class names, you can specify the ones you actually want to use. There's a partitioner command, which allows you to determine which reducer a key is sent to. So you could specify the name of the actual reducer you're going to use. For the combiner, the same thing. Which combiner executable to send the map output to can be specified. And then there are some other commands. For example, the verbose will give you a lot more information as the command runs. Command env, name equals value, in case you want to change the default configuration parameters with which we are supplying the streaming command. So what's lazy output? We'll learn more about this a little later. You'll be able to understand it when we actually try to learn what's output.collect. We haven't yet gone through that particular parameter, but as we learn more about Hadoop, we'll understand what's output.collect. But essentially, what lazy output will do is it's going to create the output file only on the first call to output.collect. So that's for some reason it's called creating the output lazily. The number of reduced tasks, so you can specify whether you want to run just one reduced task or multiple, or take the default that's configured. So if you want to specifically have more number of reduced tasks run, you can use this parameter. The map debug, it's a call. Um, you can actually call a script to be run in case your map task fails. Reduce debug similarly. So if a reduced task fails, if you want a script to be run, you can specify. So more generic options, we have libjars. This is a comma separated list of jar files to include in the class path. Archives. So if you want to include some archives which need to be unarchived on the compute machines, you have these additional options. Further on, the D option, this is important. So if you want to run your streaming job and you want to give your own temporary directories, then you can use the -d option. This is one of the uses of the -d options, but there are more. So you could specify which specific local directory or the system directory or the temp directory you want to send your files over to, the temporary files as they get created during running of the job. Um, so you can also specify how many reduced tasks you want to run. You can specify um, the tasks to be 0. If you have a 0 number of tasks, reduced tasks to be run, that means you're essentially only running the mapper job. And now we'll actually start running some examples very quickly. So the first example that we're going to run is actually going to use the cat and the wc command of Unix. So fortunately, Unix already has given us a couple of commands which we can use very effectively for the demonstration of our programs. So the cat command is nothing but a command that will output the content of any file that's applied to it. And word count is nothing but a command that sums up the number of words, the number of characters, or the number of lines that exist in a file. So these are very interesting commands that we can actually use in streaming without any changes. So for the mapper, we'll use cat. For the reducer, we'll use word count, and I'll show you how to do that in a little while. For the input folder, which is supposed to contain the files which will be supplied to our mapper, we need to specify it. We need to tell what input folder we are going to use, and we have to specify an output folder. It's important to note that the output folder should not already exist. If it already exists, our job is going to fail, because the streaming job is actually going to create the output folder on the fly for us. Another example that we're going to try today is to use the Python executables. So the Python language uh, also allows us to create some executables which can be used in Unix. So for the same type of commands, that's the cat command and the wc or the word count command, we are going to write our own Python program which will effectively do the same thing that the cat command does and the same thing that the word count command does, or at least one part of what the word count command does, that is the counting of the words. So we'll see how to do these two examples very quickly. Okay, so much for theory. So now let's do some practical examples. So what we're going to do is to use, like I said before, we're going to use two commands, the cat command of Unix as the mapper and the wc command as the reducer. So let's see first of all what exactly does the cat command do. So the cat command, if you look at it, before we do that, we see that in this current folder we've got several files. One of them is called um, the test.txt file right here. So if you want to see the contents of the test.txt file, we use the cat command, and you see we have a little file over here. It's got it's got some text in it. This is a test file, blah blah blah. And what we need to do is we'll be using this file as the input for our cat command when we run the Hadoop streaming job. So the other thing that we need to note is the wc command. So in the wc command, um, which will take the standard input as its input. So let's see, what we can do is we'll use the cat.txt command and pipe it to the wc command. And what do we get? We get this kind of an output, 742 214. So what exactly are these numbers? These are really the counts that the word count program in Unix does. And if you want to take a quick look at what all these what all does wc do, we'll just do a man wc, and it will give you all the different options that come with the word count program. You see one of them is -c, which gives you the number of bytes that a file contains. -l will give you the number of lines. -w, this gives you the number of words. So this tells us what the wc command does. So both these commands, cat and wc, take standard input as its input, and they send output to standard output. So having looked at these two commands, what else do we need for our job to run? So if you remember, we have to create a folder called inpt. If you look at this example that we are running, so we have to create a command called a folder called inpt, and this here is the command we will run, which is the Hadoop streaming command with the input folder called inpt and an output folder called otpt. So let's go back to right here. So what we can do is first of all, let's see if our Hadoop cluster is running, because now most of the things we're going to do from this point on is going to be performed on Hadoop. So let's see what's happening. Do we have the Hadoop cluster running? So JPS is a command that will actually give you information about the cluster and tell you whether it's running or not. So we see that we have a data node, name node, and everything running fine, so we should be good. The next thing we need to see is, do we have inpt folder by any chance already existing in our Hadoop cluster? So for doing that, we'll run this command ls with a -r option, which essentially means a recursive listing. And if you look at this, it's telling us that these are the folders already existing in our Hadoop cluster. We do have a test.txt, but it's not lying under any inpt folder. So what we'll do is we will, and we do see another test.txt right here in user huser folder. So we do have those files lying around in the cluster, but not exactly in the location that we want. So the first thing we'll do is we'll create a folder inpt, and to do that we use the mkdir command, and we want it to go under a specific folder called inpt. Okay. Now incidentally, /user/huser is our Hadoop home folder, and within that now we have created one called inpt. Okay, so did it get created or not? To verify that, we can run the listing command again, ls-r, and it shows us yes, that we do have that folder. Now the other thing we need to do is we want to take our local file from our local system, the file called test.txt, and put it into this input folder. And to do that, what we need to do is run this command. If you remember the put command, and the file we want to put is test.txt, and we want it to go into /user/huser/inpt folder, and let's see if that gets done. Alright, that seems to have succeeded. Double check. Now if we run the listing again, we see that yes, we do have this file in the right folder. And the next thing we need to do is, do we have an otpt folder, which is going to be our output folder after the streaming job is done? we see that we don't really have an OTPD folder, which is good because Hadoop is supposed to make it for us, and if it finds one existing, it will give us an error. So it looks like we are very good now. So since I had already copied that command, I'm going to now run it, and there it goes. Okay, beautiful. So now it's showing you that there is an output directory, and the output directory is called OTPT, where it has sent its output, and a lot of verbose information was sent out to the screen by Hadoop streaming. So now we need to just go and check and verify that we have what we want in the output directory. So what did it actually drop into the directory? To figure that out, we'll this time run um, the cat command, and we don't need the R option for this. And the file we want to view is user huser OTPT, which is a folder that it created, and we give a wildcard so that it displays everything in every file in that folder. And here you go. So it's showing you that we have this output as expected. So it did create the output for us. So it looks like our command that we ran, that was this one, it actually did pretty good. So let me just clear everything up and show you the command one more time. This was the command we ran. So we prefix it with Hadoop. We don't have to write bin/Hadoop. A lot of books will ask you to write bin/Hadoop, but bin is already in our path, so we don't have to really specify it. Hadoop and then jar, that's the command, and then we gave the full path to the streaming.jar file, and we specified our input folder as inpt, output folder as otpt, the mapper program to be cat, and reducer to be wc, and it worked perfectly well. Very good. So now that this has been done, the real thing that we want to do is to write our own programs in a different language than Java and submit it. So we need to now see how we can write a program called cat.py, and that will be our Python program. If you know that Python programs always have a suffix of py, so the extension of the file is always py. So to help us along, what I've done in this particular folder is we've already got created one wc mapper.py program, and we also have a wc reducer.py program. So um, so word count mapper, word count reducer. The mapper program in our case is going to take the inputs from whatever is given to it from standard input, and it's going to split it into all the constituent words within the file from the input. So let's take a quick look at what's there in this file. So this is our wc underscore mapper program. So there are two things very important for you to know. One is that whenever you're writing an executable program for Python and you want it to run in Unix, you got to first of all prefix this line on top, so which means you got to have hash exclamation mark and then the path to the env command and Python. So what happens when you do this is that Unix will understand that whatever is contained within this particular executable program is going to use the Python executable, and it should be present in our as an environment variable. So this is where the program lines really start for Python, that is import sys, import re. So we import these two libraries, one being system, the other being regular expression. And what it's doing is for every line that it's taking into the program, which means from standard input, any line that is sent to it. So line is a variable. All the standard input, whatever is sent to this program, will be sent to this line variable, and we do a split and a strip. So a strip and a split. So the strip is actually doing nothing but removing the leading and the trailing spaces or blanks, and the split command that's available in Python already for us is actually just splitting the file, or splitting the line, sorry, into its component words. So all the words in that line will then be existing as a list in this X variable. And then the next thing that we are doing is we are simply saying for I in X, which means for the variable I, just loop through the list elements in X and just print them out. And as we are doing that, we are also converting them to uppercase. So since Python has all these built-in functions like upper, split, and strip, so this makes our program real short out here. So this is what the program is going to be, and I'll come out of this now. Now if you were to just test this program out in Python, one thing you could do is probably try to run Python and then give the name of the program wc mapper.py, right? But it's not going to work so well because we also need to supply the input to that program. So what you could do is, let's say if you say cat and give the file name that we have like test dot txt, and we send it to the Python program. So let's see if that works. Python wc underscore mapper dot py. There you go. It does work very well. So it's showing us everything. All the words in have been now split out, and they are occurring one per line, which is very nice because so this all these different lines can now be sent to the reducer job, and the reducer will take care of counting all the words, and at this point there's no count available. This is just all the words that we have in the file. The other thing we need to notice is that right now we are saying that we are piping it to Python. What if we were to run the wcmapper.py command without using the Python word at all, right? So let's try that part and see if it works. So if we just do this, and it should work, because the reason being that in wcmapper.py, you remember on the top we had put in that one executable line that tells the compiler of Unix that this is actually a Python command to be run. So not a backslash, we need a slash, and there you go. So it works pretty good. So you see, don't have to prefix it with Python. So it looks like our wcmapper.py program is working pretty good. Now we'll see if our reducer program works good and what exactly is contained in the wc reducer program, because that's the one we are going to be using as a reducer. So let's get into this reducer program. This program, there are some comments that I fed into this just for understanding. It's also going to import those two lines again, sys and regular expressions, just in case because we are using sys.stdin, and import regular expression just in case we are actually going to compare expressions within this program and using the functions that are standard and available in Python. So at this time what we do is we write a similar kind of a loop. We again loop line by line, taking the input from standard input, and we are putting in all the words into a variable called current, and putting just a number 1, an integer 1, with every one of these every one of the words that are encountered in the line. So line by line, you remember we only have one word per line coming out from the mapper. So what this will do is for every word it's going to just put in the word comma 1, and there's a little logic out here which all it's doing is it's just checking to see if the same word is repeating one after the other multiple times in, let's say, 2 or 3 lines. Then it's going to sum them up, the same word again. So let's say if you had a word called this, so if this is there in line 1, this is there in line 2, and again the same word this is there in line 3, we want this to have a total of 3. So that's what this is doing. Now after it does the count, it just prints the output out, to standard output, and when it comes out of the loop, so then it just prints the word out and gives us the count of the word. So as long as it keeps encountering the previous word, every time it gets to the next word, it just keeps adding 1 to the count. That's right here. And as soon as the previous is not equal to the current, which means a new word has happened, then it comes out of the loop. It does this printing for the word and its count, and then it loops back again. So it keeps running through this loop over and over again. And in the very end, just to make sure we don't miss out the last word, because really what we are doing is printing out the previous word's counts, we do a final one more print, and that will print out the last word. So that's what this program's doing. But one thing you might have noticed, even the reducer program over here is not sorting our words out. If you see, there is that, the first word here, is also present over here. And what reducer is, the the WC reducer program we just saw would be expecting this that to be occurring right after this that, which means if this whole thing was sorted, we will have that occurring multiple times right there on the top. But that's not what's happening right now. Well, the good thing is we don't really have to run a sort as well before submitting it to reducer, because Hadoop is going to do that internally for us. So that's the good part about it. So it saves us some amount of coding effort. We don't have to sort it. The moment the mapper sends this output, it will automatically be sorted by Hadoop when it creates the reducer process, and it will send in a sorted output to the reducer. So all these words will actually get sorted. So if a word occurs multiple times, they will be occurring next to each other. And that's how that's the logic, that's the assumption in the logic which we wrote for the WC reducer.py program, right? So does the WC reducer.py program run okay or not? Let's try it out and see if it runs fine. So to check our WC reducer.py, we first need to give it an input, and the input has to be of this kind, and this is the output of the cat command. So we'll run this again. This time we'll run the mapper and we'll send the output of the mapper into, let's say, a file called, let's say, tmp. Okay, let's say we send the output to temp1. Okay, and now if you see, do we have a temp1? Yes, and it does have all these lines in it now. Okay, so now that we have a temp1 file which has the output from the mapper, we will send it to the reducer. And to do that, we'll do this wc underscore reducer dot py. Oops, sorry. And there you go. So you notice over here that since Unix will not do an automatic sort for you, so we are only getting test and test again and again without any count being done. It's just counting every single line and going to the next word, not finding the same word again. So it just is basically assuming that every word is basically having a count of 1. So now reducer is working fine. One thing we need to always remember is, I said there are two things, in fact. When we looked at the mapper program, I said there's a line on the top that you've got to make sure is present. The other thing that you got to make sure is that the WC mapper.py and the WC reducer.py, these two files being executables on Unix, you must have read, write, and execute permissions granted to them, both of these. So as in this case, if you see, the user has the permission of read, write, execute, whereas the group as well as the others will not have any write permission. The W is missing over here. So this shows that we have execute permissions on these two files, and in order to make sure that they do have execute permissions, the command that you need to use is either change mod plus x, and then you can give the name of the file. That's one way to do it. And if you see now, so it actually created an execute permission, but the other way, well, the permission was already existing, so it didn't really change anything. So the other way to do it is, so if I want to remove, let me remove the execute permission from the mapper, and then if you see over here, it removed right here the permission of x for the user from the mapper file. Now if I have to grant it, I can either do a plus x like I did before, and that will bring it back, see, and so you see this is back again. Or the other thing I could do is, the way I like to do is, usually I use numbers, which means I would use something like for basically the way it works in granting permissions, there are three numbers, 4, 2 and 1. So 4 stands for read, 2 for write, and 1 for execute. So if you were to give a read and write permission, 4 plus 2 means 6, so you would say 6. That would give you read and write. If you want to give read, write and execute, it would become 4 plus 2 plus 1, which means 7. So if you so for the user, that's this first part, read, write, execute. So change mode 7. For the group permission, it's read and execute only, so 4 plus 1, which makes it 5. And for others, we want to give again 5, because only read and execute needs to be given to everybody else. So we change this again, and you see, if you see it again here, the permissions have now been set perfectly. So you got to make sure that you've set the right permissions, otherwise your job will not work if these don't have execute permissions. So now we are set. We do have mapper and we have a reducer program. Now if we again paste what we did earlier, and okay, we don't want to run it this way, but it's going to fail, of course, because it's saying it's the old command again that we ran, and it's saying it's the output folder is already existing. So that reminds me about one more thing. Before we run our program with mapper and reducer, we'll make sure that we remove the output folder or give a new folder name. So this was the command that we need to run. So this time again we'll take the input from the input folder. It already has our text file in it. Output will retain same as OTPT. We want this to be run. For mapper, instead of cat, now this time we are going to run wc mapper mapper.py, and for our reducer we're going to use wc reducer.py. So both our Python programs are going to be used by Hadoop. This program will fail at this point because we have the output folder already there, and what we need to do is remove, see, it says streaming command failed because it found the output directory already there. So we'll first of all remove the directory, and to do that we just go and do rmdir, and then okay, don't forget to put the minus sign, and then okay, rmdir, or really we'll actually use a recursive delete of user huser um, slash OTPT. Now this is a dangerous command, I mentioned it before as well. So this is going to recursively delete everything under OTPT folder, which means OTPT will vanish and every subfolder under it, all the files under it are going to get deleted. And not only OTPT, every other folder under OTPT with all the files will be wiped clean. So it deleted it. Make sure that we have everything in place now. So we'll rerun what we ran earlier, recursively see what we've got. So it's showing now that we do have an inpt folder which has a test.txt file already in there, and now we need to, and there's no OTPT folder, which is good. We want Hadoop to create it for us. So now we'll run the streaming command, this one, with the reducer and the mapper coming from Python. So we run this command. It's doing a great job. It just ran perfectly well. A lot of verbose output, and finally it says output directory OTPT created. So let's just go and see if we have everything created perfectly well. So again, now we see that there is an OTPT folder, and so I'll copy this whole path and see what's there in this file that it created for us. Shift Control C, Shift Control V, and we need to have Hadoop FS, and we'll cat the contents, and we do a Shift Control V. Look what's inside it. There you go. And now it's showing you very clearly the totals of all the words that it's finding out there. So file has a total of 2, the has a total of 3, and has a total of 2. So it works pretty good. So it's done all these totaling for us, and this is exactly the output that we needed. So very good. So essentially this time it sorted the output on its own that came from mapper, so that our reducer program was able to loop through every single occurrence of that word in a sequence and figure out the total and throw it out into the output. So that's what's been happening in this program. Very good. So now this is all done. I think we are done with this particular session, except for just one final thing that I want to point out. There is an exercise which is essentially asking you to do a couple of things. It basically wants us to run the same program again as we ran, but using maybe some other language, like perhaps we could use Ruby. And what we want the program to do is to take a line of words as input, just as we did just now, break it out into its constituent words, which is what we did, and print them out one per line in uppercase letters. And after doing that, we want the program to take that output, which came from the first part of the exercise, and then print out a count of all the words which have been obtained. And so after doing that, the last part would be to take the program from 1 and 2, both the previous exercises, and to use the Hadoop streaming utility to have the output out into a folder, any folder in a Hadoop cluster. So it would be the same exercise that we did, but this time we should try to use another program like Ruby, or maybe you could use C++, or try it with any other programming language that you might be knowing. And with that, we come to the end of this session. Thank you.